Okay, yesterday I posted a video clip on YouTube, which was a composite drive shaft under a torque. But it turns out that my our license server at the university was not working. So instead of using the V56 release 2016, I ended up using a version of Catia R21, which is about 8, 9 years older than that. Uh, After I posted, I realized that there are few places where the dialog box is completely different from what you see in the newer version. Now, uh, I decided not to redo that drive shaft problem, because if you know a little bit of CATIA with some very minor adjustment, you can actually do it on R2016. This present problem that I'm doing has a lot of similarity to the other one, and it's going to be done in uh, R2016, and therefore it basically takes care of those differences in the dialog boxes that you see somewhere. It's a simple cylindrical pressure vessel which is under internal pressure, and it's usually when you have pressure vessels, there is some kind of a core, let's say aluminum core or steel core, and then you reinforce it by adding those composite layers to it. So I'm going to ignore that inner core. I'm going to assume that somehow this was done entirely of composite material, layered material, and therefore keep that in mind. Now, the other thing is, generally speaking, vessels are capped. So you not only have a hoop stress because of the internal pressure, but you also have axial stress in the body of the cylindrical body of the vessel, which comes from those and pressure. So the present video, I'm not going to actually model the ends, model the caps. Instead, I apply that axial force through an edge load to the cylindrical surface of the pressure vessel. Okay, and then tomorrow I'm going to do another video which actually the entire vessel is modeled and although the ends are capped, and I want to show you what the differences are between the two when it comes to comparing with some analytical results. Okay, now uh, so we have a pressure vessel like that, okay, which is on the surface of it. On the surface of it, there are the three layers: 15 degrees, minus 15 degrees, and 90 degrees. Okay, and the diameter of the shaft, the diameter of the vessel is 12 inches, and these are the geometrical properties, and it's internally subjected to 1000 psi. Now, in this problem, in this video, I'm not going to model the end caps, okay? And that being the case, you can ignore this line, but in the follow-up video, of course, these ends are also made of two-layered composites, which we're going to use that. So we're going to assume that the thickness of the ones that are 15 degrees and minus 15 degrees is the same, 0.05, and the thickness of the lamina or the ply, which is 90 degrees, goes circumferentially, is 0.15 inches. Okay. All right, let's move on. My modeling strategy is going to be, obviously, this is your cylindrical surface, so this is what I'm going to be modeling. And these end faces are going to be subjected to edge pressure, which is coming, or edge load actually, axial load, which are coming from hand calculation. Now, it is going to be tough to do this, something like that in Abacus, or at least maybe I don't know it, I'm not sure. Uh, uh, if you want to do it as a single cylindrical surface, now this is very easy in some of the software. So, but in this particular software, CATIA, the native solver of FEA solver of CATIA, which is Alfini, I had a hard time doing this. So my strategy is to actually uh, model this cylinder pressure vessel as two half cylinders, the top one and the bottom one. For each one of these, I will define a rosette. The only difference between the two rosettes is that in the bottom one, Z goes down, and on the top one, Z goes up, and the direction of X is also changed. This allows me easily create those plies without any glitches. Okay. So this problem that they have, they showed you because of the nature of the geometry and the loading and of course the stacking sequence, there are planes of symmetry. There are two planes of symmetry, actually three planes of symmetry, but I'm not going to use any of them, so I will model the actual vessel. The hand calculation that I was talking about comes from basic strength of material type calculation. So you can see if you take a patch out of this wall, this is basically under biaxial loading. There's no shear in that particular patch. Okay, and what I'm going to be doing is this value that you see here is called NZ, pressure times the diameter over 4, is what I'm going to be specifying on the edge, on this circular edge, without actually modeling the cap itself, front and the back. So basically, this is what I'm going to be doing. Based on the dimensions that I gave you, that thing that I'm going to be applying to the edge, circular edge on the left and on the right, is just 3,000 pound-foot per inch. Okay, and of course the internal pressure is 1000 psi. Notice that we no longer have a cap. Uh, uh, this is why we're replacing it with an equivalent static load, which is this edge load. Okay, now we're going to be comparing our results with some excellent series of lectures at East Carolina. There's the link. In fact, based on these material properties, which are the carbon epoxy, the calculation has been done. So for the 15-degree ply, these are supposed to be the stresses along the fiber and transverse. And of course, the minus 15-degree ply is going to be the same thing, except the sign of the shear is going to be reversed, and the 90-degree ply is going to be like this. Now notice that for all practical purposes, these are zeros compared to those other two numbers because the orders of magnitude smaller. Okay, so von Mises stress for the two 15 and minus 15 is going to be the same, roughly 27,000 psi, and for the 90-degree ply it's going to be 36,000 psi. So we're going to be comparing our Catia FEA results with these numbers. Okay. All right, let's move on and make it. So I'm going to keep this thing handy here, down below. First thing, because I have two different thicknesses for these different plies, in other words, 0.05 inch for the 15 degree and minus 15 degree, and 0.15 for the 90 degree ply, I'm going to create two materials. The properties are the same except for the cured thickness. So let's go ahead and do this thing at infrastructure, material library. I'm going to create one. So this one, let me first of all call this thing, so I will call it carbon epoxy, and 0.05 inch, right? The thick 0.05 inch as the cured thickness, basically. So apply. So notice that the name changes here. And then for composite, we're going to say unidirectional, okay, unidirectional, and this is going to be the cured thickness is going to be 0.05 inches. Okay, so that's this. And then for analysis, we're going to use 2D orthotropic. We input the parameters here. This is 20 e to the 6, 20 e to the 6, This one is 1.2 e to the 6. For Poisson ratio, 0.25. See 0.25. Shear modulus 0.8 e to the 6. And for the other two, I'm going to use half of this. We don't need the other two for this problem, but I'm going to put half of the first shear modulus, 0.4 e to the 6. Okay, very good. Since we are not using the strength properties for detecting failure and things like that, this is all we need. Apply and OK. Now the other one is going to be exactly like that, except that the Q thickness is 0.15. So I'm going to copy this, copy and paste it. We'll try it again. Copy, paste. I'm going to move this thing down here so that we can see it better. The only thing I'm going to change here is its name. So it's no longer copy of that. It's carbon epoxy, and the thickness, Q thickness is 0.15. And I'm going to set that value. So under the composite, this is going to be 0.15 instead of 0.05. Okay. And apply. And then I don't have to input these things because they're the same values. Okay, good. So we say all right, and now we're going to save this thing. We're going to save this thing in that folder that I have created on my desktop. What is that? It was called pressure vessel. Let me see now. I thought I don't see the name, so I'm going to create actually what I want. So we're going to say new folder, pressure vessel, PV ends not modeled. So that uh, uh, pressure vessels right there, and it's not modeled. And this library that I created, why don't I give it a name to material one? How about calling it pressure vessel? Pressure vessel. It's going to go into that folder. Everything that I made is going to go into that folder, so including my material library. So I'm going to close this. Now we're going to start our part. So let's start with the part file. I'll give it the name a pressure vessel ends not modeled. Ends not modeled. Too many D's here. Okay, and immediately save it. So file, save management, save as. On the desktop, I have that folder that I just put my material library in it. We say OK, and we close it. Okay, so all right, I noticed that these planes are very small. So of course I can zoom in, but something is not right here. Let me see if I can change the plane size. So tools, options. I didn't expect to run into this problem, but it's okay. We'll find it. Infrastructure, uh, infrastructure, mechanic, part infrastructure, part design. Well, actually not there. Sorry. Infrastructure, part infrastructure. Part infrastructure right there, and display. This access system and play. Maybe I changed this thing, so we'll see how it looks like. There. Oh, whew. Okay. So save it. Now, notice that my strategy is to make these two pieces. Okay. So the radius here is 6, and the length is 40 inches. So we go there. We go to uh, the YZ plane sketch. You have to be in generative shape design to create surfaces and things like that. So we're going to sketch. Okay, circle. That. Okay. I noticed that because of my uh, made some changes here, so that's why grid size and things like that looks weird. So let me first fix this thing. Let's put some dimension here. This is supposed to be 6 inches, right? 6 inches and fit. That's a lot better. And I just noticed that this point is not exactly on that line. So this point control that axis. We're going to make it coincident. There. Very good. So exit. And then we're going to extrude that. There's the extrude. Mirror extent. And 20 inches in each direction, so that gives you a total length of 40 there. Okay. Now, if you watched my earlier videos, you notice that I always join this thing, because when I join, you will give basically the surface a direction. In this case, direction arrow up, and I flip this so that it goes down. And when you do this, in other words, you give it a direction. In this case, I made it down. When you create shell elements, the normal to the shell elements always goes opposite to the normal to this join entity. Okay, which means you have a control. You're not going to get unexpected, normals to the shell elements. Okay, so the next thing I want to do, I want to extract the boundary of this. So you go to this, where is the boundary? Let me move this thing out. The same place that you see the joint right there. There's the boundary. See this? This is the boundary. You click on it and you select that joint surface, and it extracts the boundary. Okay, so there. And that's pretty much it. The only thing I'm going to do is I'm going to rename all of these to say top. So right click, properties, top. This is for bookkeeping purposes. You always know what you're picking later on. So properties, top, properties, top. And the last one, boundary, also top. Now I also will, at this point, I also will create a coordinate system, axis system, which I'm going to call top. So there is the place that you use axis system. See axis system, you click on it. Now, ordinarily, it places it at the global origin. You can see that it's right there with Z pointing up, X aligned with the global XYZ. Now this is fine, there's nothing wrong with it, except that what I would like to do is I would like to move this thing a little bit higher so that it doesn't clog the picture, okay? Either higher or, yeah, maybe that's a good idea. So I'm going to say, put the cursor there, right click, create a point, and I will, not on a curve, with coordinates, okay? So the height of it, I'm going to make it, remember the radius was 6, so height of it, I'm going to make it 10. So that point origin is going to be way up there. Preview, so it's going to be right up there, maybe even higher, 15, right. And say, okay, I'm happy with this, except that I don't want this thing to be my current coordinate system. So I'll uncheck this thing, it becomes solid, it becomes dash. That means that your global, still the global coordinate system with origin sitting down here is still the global coordinate system. Like while we're at it, we're going to rename this thing also to say top. So properties top. I will repeat exactly the same thing for the bottom piece, okay? So once again, on the YZ plane, we'll sketch another circle like that, semicircle like that. There we are. Give it a dimension. It was 6 inches. 6 inches. Okay, exit. And then we're going to extrude it. There's the extrude. These numbers are the same as before, so it does it correctly. Okay, and then I'm going to join it. You click on the join, click on the bottom surface, and just to double check, you click on it, you see that the arrow is going to be pointing away from that surface. I click on it so that it goes towards the inside of the cylinder. And finally, the boundary. There's the boundary. See that? There's the boundary. And you select this thing that you joined. The boundary is going to be extracted, and you're going to say, okay. The reason that we need these boundaries is because later on we're going to create plies, and I'm going to do that manually for you, although it's a laborious process. You have to do it, I don't know, 6 times, 5 times, and but you have a better control. You can do it with zone method and things like that. You just leave it the way it is. Okay, so let me call this thing top. Sorry, bottom. So properties bottom, BOT, properties BOT, join, we're going to make it BOT, and boundary, we're going to make it BOT. These steps are not necessary, but it allows you to have a better idea when you pick something what they are. Then we're going to create our coordinate system, create a point. Notice that I already have the set, not on the curve, by coordinates. I already have my 15 here, so I make this thing minus 15, and it will create a point down there, except that, first of all, I want Z to point down. Remember, the other one is up here, right? I want Z to point down, so I put the cursor on the Y-axis, right-click, and rotation. And if you rotate by 180 degrees, 180 degrees, that will minus 180 degrees. It'll take care of it the way I want, minus 180. Notice that Z is down, X is going to the right, exactly what I wanted, and we say okay. Now why don't we also call this thing bottom? Right click, properties, BOT. Okay, very good. Okay, so save everything. We are pretty much done as far as the creating the model is concerned. So let me go ahead and switch to the mechanical design and what is that? Composite design. First thing we're going to do is to create our parameter, composite parameters right there. Add the material. We're going to go to that library that I created. It was on my desktop. and it was called pressure vessel ends not modeled. There's my material library. Remember I created this? You say okay. They'll tell you that there are two materials in there, and I want both of them to be used. Okay, so I say okay. That's the one with the acute thickness of 0.05. And then again, add material, acute thickness of 0.15, which is going to be used for the 90-degree ply. Okay, very good. Now here, we also have to create a rosette, add a rosette. Now, these are going to be used as my rosette. So add a rosette. And axis system is, I'm doing the top one, right? So there we are. And you have a choice of Cartesian. There is no cylindrical here. If you go to the drive shaft video segment that I already posted, this window looks a little bit different. It's a cylindrical sorry, Cartesian or cylindrical. Here they have added a few things, and you can do cylindrical here too, but I'm not going to worry about that. Notice that the good thing is that when I selected Rosette 1, it created top axis system. Why don't actually, while I'm here, why don't I give this thing the name top Rosette? How about that? Top Rosette. I think it is double T. Okay, nothing else. So it's Cartesian. Everything is good. We say okay, and add another one. This time we use this bottom one, and I will call it the bottom rosette, BOT rosette. And again, it's Cartesian, so we say fine. So the two rosettes are created also. This window also looks different, okay? So if you're using older versions, R21 and prior to that, you have to do the same thing, but the dialog boxes are going to be different. And we say, okay, so we don't need these rosettes. I'm going to hide them. Hide and hide. Excellent. So save, do a save. And now we're going to create our plies. The first thing is we're going to create a ply group for the top section. So select it. Surface is of course here. Notice that the top surface is selected. The name of this, I'm going to change this in top ply group basically. And the direction of the draping is downward. I want to stack them in the upward direction. So flip it. Notice that it flipped right there. You can see that. Flip. And for the rosette, I'm going to select top rosette. Okay. And that's pretty much it. So we say okay. While we're at it, we might as well create the bottom one and then we create our ply. So here is the other ply group. So we're going to call it bottom, BOT. For surface is the bottom surface. Flip the direction so it's stacked outward. And for the rosette, I'm going to select the bottom rosette. And that's pretty much it. Okay. Now we're going to create our plies. So let's work on top one first. You click on the on this ply. It says go and select your ply group. So I'm going to do the top one first. Notice that there's going to be ply one. Now for the boundary, for the curve of the contour, I can go and select that top boundary that I extracted. See that? And then attribute is going to be 45 degree. The first one is 45 degree. I don't have to worry about top rosette because it's already selected automatically. Notice that the ply is created here, right there. You can see that. Let's do another one. Again, the same ply group. The boundary is still the same as what was up there, the top. The attribute is going to be minus 45. Okay, the third one, the third ply in that group, top group, boundary is still the same. And for the attribute, we're going to say 90 degrees. Now notice that this is a kind of laborious process. So it was easier if we created these plies using a zone. If you had 50 of these, then you really don't want to do it 50 times, although you can actually copy and paste plies. But anyway, this is a simple problem. That's all right. Now let's do the plies for the bottom group. So click on the apply, manual apply, you select it. And for the boundary, for the contour, you're going to take the bottom bottom boundary, and for the attributes again it's minus 45 first. Okay, yeah, and next one, same group, the boundary is BOT, attribute is minus 45. Oh, I don't know why I said 45. This should have been 15, right? So okay, I made a mistake, so we're gonna fix it, don't worry about it. Okay, let's do the last one. The last one is actually still 19. So their boundary is BOT, attribute is 90. We say okay. I made a mistake because I thought these were 45-degree plies. Actually, they were 15 and minus 15. So we can always go and fix it. So we go back to composite parameter here, and under directions, these are the default one. I want to add 15 and minus 15 to it. So I add a direction. I say 15 and 15. The value is 15. Let me change the color because later on I want to be able to see these things. Another one, minus 15, minus 15, and value minus 15 here. And the color, I'm going to make it darker brown. So we say okay. We say all right. Now, what we have to do, unfortunately, I have to change my ply angle. So I go to this ply 1. Under attribute, instead of 15, it is plus 15. Instead of 45, it's 15. And I go to the second ply. And for attribute, I choose minus 15. And I have to do the same thing for the first two plies in this other group. So for attribute, instead of 45, I want 15. And this other one is also, instead of minus 45, I want minus 50. Okay, I didn't mean this thing to happen, but it's good if you didn't know how to do it, or if you wanted to make another practice, we just did it. All right, let's save everything. Let's check actually. So you can go and select the ply exploder. I have two groups. The top group, it should be 15, in other words, brown, darker brown, and then 90, I think it's maybe blue, I don't know, let's find out. There, yeah, okay. Let's change the scale here so that we can see it better. We may make it 20, apply, yeah. So you can see that it is 15 minus 15 and 90. And if you go to the bottom one, same thing should happen. There we are. If you want both of them to show at the same time, apply, there. Okay, so they match, cancel. Very good, save. Now we are pretty much done as far as the modeling for the composite is concerned. Now we're going to go to generative structure analysis and mesh this thing. I want a fancy mesh, so instead of going to generative structure analysis, I'll go to advanced meshing tool. Just like I did in many other videos before, we say okay. We're going to use the surface mesher right there. Select the top. 0.15, I'll leave it at 0.15 and then we see if it's too fine, we're going to change it. And then zap it or mesh it. And there we are. I think this is too fine. Yeah. So can say okay and exit. But what I can do is I can double click on this surface mesher that I created. I'm going to change this thing to 1. by the way, parabolic and quad only, and then mesh it, zap it. There we are. Visualize, exit, and I do the same thing to the bottom one, surface measure, the bottom joint surface. Everything is the same. Mesh it. I say OK, and exit. Now it's a good idea if I change these names too. So this one is the top one, top, and this one is the bottom one, properties, bottom one, BOT. Okay, so now we're going to go to generative structure analysis to apply the loads and restraints and properties. You have to go there. You have no other choice. Advanced meshing tool is only for meshing. If you want to see your mesh, you can put the cursor there, right-click mesh visualization, and there we are. If you're happy, just uncheck that, deactivate that. Okay, good. So let us actually apply properties, composite properties. So imported composite property. It's asking you what's the, let's do the top layer first, or top part first. So the support is going to be this thing on the top, and for the ply, you're going to go to your tree and select top. Okay, remember you have two ply groups. So the top one is what we're doing now. We say OK, and the symmetry means that it's going to be stacked symmetrically about this surface. We talked about this symmetrical checkbox in other videos. If you want, you can look at it and do it again. So the bottom surface, ply, and bottom group. Say OK, keep it symmetric, and we say OK. Notice that the properties are created here. This is the first one, and this is the second one. Why don't I give these things meaningful names too? This is going to be top, and this is going to be bottom. Properties, BOT. BOT. You say OK. All right, by the way, once you specify the properties without even applying loads and restraints and things like that, you can actually check and see whether these are the directions are correct. So so what you can do is you can put the cursor, on properties right there. See that? Properties, right click. Oh, before I do this, before I show these direction, I know that I don't have any loads and restraints. I understand that, but we can always say run and show me the mesh only, because I don't have anything else. And it did it. Now, when you put the cursor here, right click, you see some other stuff showing at the bottom. So generate image, composite angle, symbol, and you say okay. Okay, so there we are, except that let me unhide the part because it's easier to see what's going on. There we are. Okay, so notice that these are the 15 degrees on the top, 15 degrees at the bottom, and the choice of the rosette, direction of the rosette and things like that, if you don't do that, these won't line up, okay? So I talked about this thing in the shaft, in the the shaft, driver shaft video, okay? So you can look at it, but this is okay. So now you can also look at the other layers. So if you go here, so if you go, say, not the mesh, what I want it here, right here. Double click on composite angle, more. This was layer one. This was layer one. If you go to layer two, notice that the direction changes. See that? Let me bring these closer to you. The direction changes. And layer three, of course, is all going to be 90 degrees. You can see that. Okay. All right. We say okay. The reason that this color change is because I'm showing the mesh. I don't want to show the mesh, so let me deactivate this mesh. Okay, let me unhide my part. It's easier to see it on a different background. There we are. This was ply 3, composite angle in ply 3. Let's try it again. Let's try 2. And as I said, these directions match 15 degrees, 15 degrees, the lines match. Okay, so we're good. Deactivate this guy. All right, so let's go ahead and apply our loads. Okay, so pressure, there's a pressure, minus 1000. If the direction is not right, we're going to fix it. So I'll select the top face and the bottom face. Notice that uh, the, if I change this thing, to plus, these are going to go point down. That is true. However, it also has with the direction of those joins that I flipped. Okay. So all I'm saying is that look at your drawing, look at your screen, make sure it is what you want. Okay. So that's all I want to say here. Okay. Good. Now on this edge, on these two, on these, I'm going to apply a load of 3,000 pound per inch, edge load of 3,000 pound per inch. Okay. So what we're going to do is there is how you do edge load right there, line force density. So I'm going to select. Oh, look, I can't pick it. The reason you can't pick it is because those plies are blocking. Those plies are showing here. So go and hide your stacking sequence. Hide this. And these boundaries are also showing. So go to your part. Hide the top. Hide the top. Notice that now it's a black line. And hide the bottom boundary. This is a black line. Now you can apply your edge load. So on this top, on this, in the direction X, let's put down 3,000 LBF underscore inch. And I'm sure it's going to translate into this number Newton meter. Did it? Let me try one more time. 3,000, maybe this is correct, I don't know. LBF underscore inch. Let's see if it becomes 52,000 again. Yeah, that looks good. Okay, so well, actually I can do it on both of these at the same time, simultaneously on these. Okay, yep. So we say okay. Oh, what is it asking? Oh, it act in the previous run that I made, my coordinate system was user, but I want global here, right? The reason that this was I could not close this is that there was a user coordinate system here that for I was using in the last run and I needed it, so this does not reset. So we say okay, and if you look closely, you see that the edge load is put in there in the proper direction. Now I go and do exactly the same thing on the other side. So edge load on this edge and that edge, and the only difference is that, oh, this is distributed force. That's wrong, sorry. Edge load is right here. Line force density is here, the one that I just did. Top one and the bottom one. And the only thing I'm going to do is put a minus sign there so that it pressurized, because it's pressurized, so it's going to go in the other direction. There. So if you look closely, you see that it is around that edge. This is not at these 2 points. It's on that edge. It's the density, force density on that. Now, if I run this thing, it is not going to work because this is free as a rigid body motion. This can move as a rigid body motion. And we have talked about this thing on numerous occasions. I can apply, I have to take away the rigid body motion by applying something like the 1, 2, 3 rule, or I don't want to say cheat, but I can cheat and use the isostatic constraints, which automatically applies that 1, 2, 3 rule for you, but it doesn't tell you where it applied. So you got to be careful about this thing. Sometimes it's abused. So I suggest that you look at the video segments which deal with this isostatic restraint and 1, 2, 3 rule. It's not going to be in the composite playlist, but it's going to be in the general FEA playlist. You click on it, notice that you don't have to pick anything. All it does is kind of automatically put this symbol on both of these pieces. Okay, before we run, I suggest we go and save. So file, Save management, analysis, save as. In that same folder, pressure vessel ends not model, analysis 1. Okay, fine. It's going to go there. And now we're going to run it, compute, and don't make sure it's not mesh only, it's all. That mesh only, you need, in order to see the direction of those arrows, the composite arrows, symbols, you have to run it either all or with mesh. So always pray. Hopefully nothing unexpected will happen. Excellent. So first look at the deformation, displacement. You click on this, and there we are. Let's change the visualization to average ISO, and I already have stuff that I don't like here, but anyway, we'll find out what the issue is. Also, this was displacement. Yeah, actually, displacement may be okay. So this is fine. This may be okay. We'll see. Now, okay. I don't particularly like what I see here, so let's plot the stresses and see what we get. Okay, so to plot the stresses, notice that the stresses are not active here. Look, this is the only place where you can plot the stresses, right? You can also do it somewhere else, but you know, the way we plot the stresses in composites, we put the cursor there. First of all, let me, not there. Go to static case, static solution case, undo this, uncheck that. Okay. As I said, I don't like those that pattern that I saw, but we'll find out what the issue is in a few minutes. Okay, so we put the cursor on static case solution, right click, we say generate mesh, and filter it with stress according to the stress, and select the say elements components. Looks like that. Double click on it, but select the double click on this thing, or on this on the contour, and select Mises. Okay, very good. Wow, that looks good. So first of all, let me change the shading to non-smooth. Okay. Well, first of all, if you see this color is 2 point, you know, somewhere up there between 2.98 and 2.83. But you know what I'm going to do is I'm going to make a box here, just show the stuff away from the ends. Okay, so how do we do that? We create a box group. There we are. This is a box group. It creates a box. You can resize it, you can move it around, etc. This is perfectly okay with me. You can resize it by selecting on this and getting these arrows and moving it around and translating. But this is good enough. So here, we'll go back to that von Mises stress, and I say, look, don't show, first of all, don't show me the deformed shape. So uncheck that. Notice that this is the undeformed shape. But then you go on the selection, say, don't show me everything. Just give me the stuff in the box group right there, and hide the box. Hide the box. Whoa, look at these numbers. 2.85 or 2.86, 10 to the 4. Now, if you go to, this was, which layer is this, by the way? This was layer 1. If you go to my last page, this is not very far from here, okay? The theoretical solution for 15%, 15-degree ply is going to be roughly 27,000, 2.7, 10 to the 4. And this guy is going to give it to you as 2.8, 10 to the 4. So it's a pretty decent approximation, okay? Now, if you go to layer 2, almost the same, okay? We expect that because these are supposed to be the same in theory. They're almost the same. And if you go to layer 3, layer 3 Now, I don't like that. This is 10 to the 5, and I don't like that. So let's go back here. This is supposed to be uh, 3.6, 10 to the 4, 36,000, and this fellow is coming out to be 100,000. So we must have done something wrong. Let's go ahead and find out, make sure everything is okay. Okay, so you remember I saw that when I saw that deformation pattern, I didn't like. I told you I didn't like it, and you can see that the von Mises stress in layer 3 in the apply 3 is actually way off. Now, what I suggest is we go and check our ply information, and for example, look at the ply 1, uh, carbon epoxy thickness 0.05, 15 degrees. That's correct. Ply 2 attributes carbon epoxy thickness 0.05 and angle minus 15, and ply 3 is supposed to be 90 with a, there it is. See, it's 90 degrees, but the material, when I was creating my ply, I didn't realize that I had a different material. That's very easy to fix. These have to be fixed, the one 90 degrees. So I'm going to double click on ply number 3, double click on ply number 3. I go to attribute. It should not be this one because this material is for 0.05 inch thickness. It should be the other one, 0.15. That's good. And I'm pretty sure I did the same mistake in that ply number 6, which is down below here. So I'm going to double click on ply number 6, go to attributes. Yeah, see, this is the wrong material. The material, of course, is the same, but remember, the cured thickness was different. When I was creating these things, inadvertently, I left this to be 0.05. So we say OK, and now we're going to run it again. So back to generative structure analysis. We're going to run. Done. So let's look at our deformation first. Uh, Deactivate this. Activate deformation. What I do suggest, although this should have taken care of it, but I suggest that we go to our properties and change them. Uh, So let's go. Let's do it like this. Double click on top. This is properties. So okay, we got to deactivate this guy first. Cancel that. Deactivate this. Okay, so double click on. Maybe easier if I just deleted this instead of. Okay, let me delete this. Okay, so let's go ahead and import composite properties. The top surface for ply. Now we're going to select ply group 1, or which was called top, and okay, and do it again. Import properties, the bottom one for ply. Go and select the bottom one right there. Say okay. Say okay, and let's go and run it now. Okay. I didn't expect this thing to happen. I would have thought that these would actually go ahead and use the proper material, but because I changed it. But so let's look at this. Activate deformation. This is better. You see that? This is a lot better. Now deactivate this fellow. Activate von Mises stress. Okay, this is a lot better. So double click. Let's go to ply number 1 first. Ply number 1. And what are we getting? 2.74. What's the hand calculation says? 2.7, pretty much 4. That's for ply 1. Same thing for ply 2. Let's go to ply 2. Nothing changed. Same thing. Ply 3. is 3.63, and that's exactly what we've got here, pretty much exactly what we got here. Now, uh, this is fine. If you want to see these stresses, one way to do that is to go and say, okay, show me, put the cursor on a static solution, right click, generate image, uh, uh, filter by stress. For example, principal, uh, well, actually, let's get the full tensor component. Okay, so double click on it and then select, for example, under visualizing, select the principal absolute values. Okay, and also show me just the box. Good. See that? 28,600. 28,600. If you want to look at the other component, look at C22, 2,640, 2,582. And C2C, well, of course, this is not the principal component. Yeah, so that's pretty much it. Good luck. I'm sorry for this mistake that I made as I was doing things. My material, inadvertently, I didn't change it to the one that went with the 90-degree ply. Good luck.